So welcome everyone to week number 4. This week we are going to focus on a single cryptographic task called privacy amplification. Privacy amplification usually forms the last step in most key distribution protocols. It's going to be very useful because it lets us reduce the task of producing a key that's uniformly random and uncorrelated from the eavesdropper to the weaker task of generating a key that has some amount of uncertainty with respect to the eavesdropper. So this idea that such an amplification of privacy could be possible, this is an idea that was first introduced by Bennett, Brassard, the inventors of quantum key distribution, with their collaborator Robert in the late 80s. Here I put for you the title and abstract of their paper. I encourage you to pause the video right now and read the whole abstract because it's a great introduction to the task of privacy amplification. Maybe let me just focus on the one important sentence here that succinctly describes the task. So it says it here: let us assume that Alice and Bob wish to agree on a secret random bit string. So that's the ultimate goal, generating the key, which should be uniformly random. What do they have at their disposal in order to achieve this task? Two things: an imperfect private channel and a perfect public channel. So these two resources are going to come out of the key distribution protocol. The perfect public channel is something that they'll always have. We'll call it an authenticated channel. And the imperfect private channel, this is going to be implemented by all the prior stages of the key distribution protocol. But focusing just on privacy amplification for this week, we just imagine that we have these two things: imperfect private channel, perfect public channel. We'll see next week how using quantum information we can implement this imperfect private channel. So let me set things up in a little bit more detail. Let's have a picture. So what's the goal? We first imagine that we have a string x. This string x will be distributed in 0, 1, n. So it's a n-bit string, and it has a certain distribution, px. It could be uniformly distributed or it could be not uniformly distributed. So this string x is communicated to both Alice and Bob. So this string x was generated using the imperfect private channel, and this is why it's not uniformly distributed. It also is the case that on this imperfect private channel or public channel that's used to communicate x to both Alice and Bob, eavesdropper Eve might have been listening in and could have kept some side information about the string x. So think, for instance, that E could be the first bit of x, x1. Or, for instance, E could contain all the even bits of x, x2, x4, x6, etc. Another example is that E could contain the parity of those bits, x2 plus also x1, x2, x3, etc. In general, E could even be a quantum state, and that quantum state is a state Rho xe that depends on x. For instance, it could be an encoding of x in the computational basis or the Hadamard basis, or maybe a mix of these two bases. So any kind of side information that the eavesdropper has kept. And the goal of privacy amplification is for Alice and Bob to perform a certain procedure. This procedure is allowed to use the public channel, so it can involve communication between Alice and Bob. But at the end of the procedure, it should be the case that Alice produces a string R. This will be a string that has length m, and m will typically be smaller than n, so some of the string x has to be discarded. Alice should come up with R. Bob should come up with the same R, and the goal is that the secrecy has been amplified. We want this string R to be uniformly distributed, approximately, and more than that, it should be uncorrelated with eavesdropper's side information. So it should be the case that if I look at the joint state of R and the eavesdropper, there's going to be a CQ state in general, R being classical, E being quantum. This state should look like approximately uniformly distributed on the R system tensor product with whatever is left over at the eavesdropper. But what's important here is that we're saying that the state is in the tensor product, meaning that the string R is uncorrelated from the eavesdropper's side information. So that's the goal of privacy amplification. Let me make these desiderata a little bit more precise. So here we are, same setup as before. Alice has a string X, Bob has a string X, and the eavesdropper has some side information E. So that's the setup. We have a state Rho XE, which is classical on X, quantum on E, and that's a state that's given as input to the procedure of privacy amplification. And then the goal of privacy amplification is to design a protocol that involves communication between Alice and Bob, such that at the end of the protocol, Alice comes up with a string RA, Bob with a string RB, such that two things should hold. First of all, we'd like the protocol to be correct, and here what correctness means is simply that Alice and Bob come up with the same string. So the probability that RA is different from RB should be less than epsilon c, where epsilon c will be the correctness parameter. And then we also want security or secrecy, and this should say that if I look at the joint state of, let's say, Alice's output, anyways it's the same as Bob's output, and the eavesdropper side information, then this should be indistinguishable using the trace distance measure up to some security error epsilon s from the totally mixed state on Alice's system tensor product with the eavesdropper side information. And that's the secrecy requirement. Now a couple things. First of all, I mentioned public communication here. What this means is that the eavesdropper can listen in and has access to the public information that's shared. So let's call K all the information that's exchanged on this public channel. Then I want not only that R is independent from the eavesdropper's initial side information E, but it should actually be independent from the updated side information, which includes the public discussion. So the proper notion of security should involve K here and here. K should also be uncorrelated with the eavesdropper's side information. This is quite important. The second thing is that we're not going to be able to achieve this if there's no assumption at all on the initial CQ state. Because if, for instance, E contains a direct copy of X, then we won't be able to extract any uniform bits. So there's going to be an assumption, and the assumption is going to be that there is some uncertainty, as measured by the min entropy that you learned about last week, of X conditioned on E, and this will be some parameter K. So we'll assume that this min entropy is large enough, and then we should have a protocol that is epsilon correct and epsilon secret for some epsilon c and some epsilon s. And in that case, we'll say that we've achieved privacy amplification for weak secrets that have entropy at least k. So that's the task. Now, this public communication here that's required between Alice and Bob, do we really need it? Because it's making the task a little bit more complicated, right? Anything that they say between them, that they exchange, is going to be leaked to the eavesdropper. So the eavesdropper has more information and makes the task more complicated. Do we really need to communicate in the first place? Let me end this module by arguing that yes, the communication is needed. How do we see this? Well, let's assume that there is no communication. So Alice locally comes up with a string RA, Bob locally comes up with a string RB. Now, if we want these two strings to be equal, then it means that the process by which you construct R from X has to be deterministic. Now, suppose that we have a deterministic protocol that somehow reduces the length of X in order to produce something that's independent of the eavesdropper. For instance, if the eavesdropper has the first bit, we could say, well, let's just drop the first bit. The problem is, we don't know what information the eavesdropper has. So let's imagine that R is computed as a function of X for some fixed deterministic function f. And then I claim that the eavesdropper can always break this. What's the idea? Well, we could just simply take as side information for the eavesdropper the first bit of f of x. So that's just one bit of side information. It's something that the eavesdropper could keep. It's just one bit. I'm assuming that f is a public function, right? The protocol, everyone knows what the protocol is, and if the function that's applied is always the same, then the eavesdropper also knows what function is going to be applied. So when X is distributed over to Alice and Bob, and the eavesdropper can listen in on this channel and keep a little bit of side information, then it could just store this first bit of fx1, and that's just one bit, but it's the first bit of R, and which means that it's enough to distinguish R from uniform, so we don't get a security guarantee. So this means that we need randomness. But if there is randomness, then there needs to be synchronization, because we want Alice and Bob to come up with the same string, RA and RB, so they can't just use their own randomized procedures. This wouldn't make them come up with the same result. And so if they need to synchronize, they need to interact. So this interaction is absolutely needed. It's going to make our task a little bit harder, but it's needed. And what we'll see is that it's possible to achieve privacy amplification using only one-way communication. So in the end, there will be a single message, Y, sent from Alice to Bob. So it's not going to be that bad, and we'll see this in the next module.